All right, so this is just a problem of combining like terms, but we're combining this with some distributive property. And what I mean by distributive property is that whenever we take this expression here and we subtract this other expression, we're subtracting every single term inside the parentheses. So in a sense, we've got our distributive property going on where we need to distribute this minus to every single one of those terms. So let's look at this. I've got, if I drop the parentheses from the first one, that's a plus 2b plus 3c. Now I'm going to subtract 4a. And most people didn't have a problem with that. Now, what I'm going to do next is I have to subtract, look at that, I'm subtracting that middle term as well. So I'm going to subtract 6b. And this is where a lot of you made your mistake. You just did the minus 4a and then you added 6b. But we're actually subtracting 6b also because that distributive property means we're subtracting each one of those terms. And then that also means I'm going to subtract negative 5c. So if I subtract negative 5c, that's the same as adding 5c. So that's how the distributive property will work out. And you have potentially already done some stuff like this in the past, but you will definitely be doing more of this when you get into algebra 2 or whatever your next math is, because you're going to be expanding polynomials. And that's if I give you a problem like 3a plus 4 times 2a squared plus 3a plus 9, right? And you expand this out. We're not going to do this problem, but there's going to be combining like terms. And that's exactly what we're doing here. So if we come back to this one that we're working on, a and a can combine. So a minus 4a is going to get negative 3a. 2b and negative 6b combine to give me negative 4b. And finally, the c's can combine. That's going to be 3c plus 5c gives me 8c. So there's the answer. Negative 3a minus 4b plus 8c, which is that answer right there. And if you made a mistake, no big deal. Hopefully you can catch what went wrong. And, that's what the purpose of this bell work is all about. All right, so yesterday we were looking at trigonometry problems in general. I know Delta Math was acting up a little bit, but it started working and you should have been able to access that practice, get some good practice in. Today we're going to be looking at word problems, and we did look at one yesterday. Now there's two things to think about with two important reasons for looking at word problems. One is that it gives us a little bit of practice as far as abstracting from words and creating equations that we can then just use our algebra skills to solve. So that's going to be important. But also it gives us an idea on how to apply trigonometry in the real world. And it has so many applications. And in a regular school year, part of my class period would be spending time going through and saying, here are different ways it's used in the real world. Honestly, I'm kind of skipping that this year, but I'm hoping just through the word problems, you can get a feel for different applications. And sure, you might read a problem and say, oh, I'll never be in that situation, so therefore it's useless. Well, sure, you might not be in that situation, but you can imagine that someone could be in that situation, and therefore trigonometry is helpful. You can imagine ways that this could apply for you, okay? So I encourage you to use your imagination to find the usefulness of trigonometry as we go through this. And we did see one yesterday. We did a one word problem where we were trying to figure out the height of a building. And that's a really good practical use of trigonometry where, it's not practical to actually measure the height. And what you can do instead is you can use trigonometry. It's easy to measure along the ground, to measure an angle looking up to the top of a building. And from there, it's easy to, at that point, decide or calculate what the height of the building is. Very practical. And it might not be buildings. It could be trees, especially, buildings have known heights if you look at the plans. But if you are out in the middle of the forest and you're looking for a tree of a particular height, you can keep using trigonometry until you find the tree that works. Okay, so enough of that. Let's look at just a couple of problems and then we're going to just get to the work. So someone mentioned in the chat that Delta Math is also acting up today. Luckily, your homework tonight does not require Delta Math. I will say if you need more practice just with trigonometry stuff, let me know, and I can help you out with that if you can't access Delta Math. So here's the situation. A ship out in the sea spots a lighthouse during a storm. The sailors know that the light at the top of the lighthouse is 187 feet above sea level. If sailors measure the angle up to the light to be 7.4 degrees, how far are they from the lighthouse? This would be really fantastic to know if you're out at sea, if it's the middle of a storm, and you want to make sure that you're not about to run into the coast, right? So knowing how far you are from the shore, this is a very practical thing. Now, these days we have computers that can, and radar that can tell us this, but imagine this was, 100 plus years ago, and this might be a way of navigating when you're close to shore. Okay, so when I asked this in first period, there was a little bit of confusion on what to do. So let me kind of set it up this way. We're always going to start with a right triangle. Now, I'm just drawing a right triangle, but I could make it look different. That doesn't really matter. All right, so if I asked you guys, where to put this information, this 187 feet, 7.4 degrees, maybe some of you right off the bat could tell me where that goes in the triangle. But to make it make a little more sense, I'm going to use some artistic skills here. And I'm going to draw, I want to actually model what's happening in this scenario. Out here at sea, we have a boat. All right, there's our lovely sailboat. It's just, rocking in the waves. Here we have a little sea cliff, and at the top of it, we have a lighthouse. Look at this, I'll even give little stripes, make it look nice. Okay, so there's the light up at the top. There's the cap. Okay, so there's our lighthouse. So if we can now see this scenario as a right triangle, then my question to you is, they give us some information. We know there's a right angle right here. And it tells us 187 feet. And I'll specifically read it. It says, they know that the light at the top of the lighthouse is 187 feet above sea level. So knowing that, where should I mark my 187 feet on this triangle? Should it be the bottom, the right, or the hypotenuse?
The right.
The right. Now, you don't have to actually draw a drawing. You might find it helpful, little stick figures, this and that. You might find that helpful in order to help your brain wrap your head around it. But if you can just imagine the scenario, just draw a right triangle. All right, no artistic skill required. So then it says, if sailors measure the angle up to the light to be 7.4 degrees, so where does that 7.4 degrees go? Go ahead.
Go like where the ship is at.
There you go. It goes, yeah, right here down where the ship is at. Now, did I actually draw a 7.4 degree angle? No, I didn't. And I don't really care if I did. Okay, I just drew a random right triangle and I'm just going to plug the numbers in. Okay, the last question is, how far are they from the lighthouse? So now we need to figure out where our x is. Are we trying to solve for the bottom of the triangle or the hypotenuse? Yeah. Now this is one that's a little bit ambiguous and it might not be the best phrasing. This is one where if they ask you a question on ACT, they will tend to make it very, very clear. This, when you're saying how far from the lighthouse, here we have to use our little bit of common sense. Does a boat care how far it is through the air from the light? Probably not. The boat is really concerned, how far am I from that wall? I don't want to run into it. So yeah, they're really asking how far are they in this direction. So at this point, I just want to draw this triangle again. So this is the 7.4. This is the 187. And this is x. So this is exactly the kind of problem that you guys were practicing with yesterday. So if you were able to get your practice done and you felt like you understood it, then this from here forward shouldn't be any problem. So let me just ask you guys real quick. Looking at this, no, let me do this. I'm just going to label this one and run through it. So we have the hypotenuse right there. Let me go ahead and mark that this is my right angle. So which is the opposite in this problem, 187 or x?
187.
187. Here's my reference angle. So there's the opposite, there's the adjacent. So I know the opposite. I'm solving for the adjacent. Which trig ratio do I want to use?
And
Tangent. I don't care about the hypotenuse at all. Tangent, let me write it right here. Sorry. Tangent of 7.4 degrees is going to equal the opposite, 187, over the adjacent, which is x. So remember, tangent of x is just opposite over adjacent. Now we can do the, I'll run through the algebra, but remember, we can do a little trick right here that says x is going to equal 187 divided by tangent of 7.4. It's just going to be, these two will swap places. So if that's a trick that you can remember, that works. But I want to remind you, this only works when x is in the denominator. So if you're going to just switch tangent and x every single time, it's not going to work always. It only works when x is in the denominator. But anyways, if I run through the algebra, I will erase that real quick. I'll multiply by x on both sides. We'll just make sure that this actually worked out the right way. Those cancel out. X times tangent of 7.4 equals 187 divided by the tangent of 7.4. And there it is. You can see x equals 187 divided by tangent of 7.4. That we can plug into the calculator. And now we can find the answer. You guys can write that on the screen whenever you find it. 1,439.8. And we will typically round to the nearest tenth. So that's a good spot for it to be, to show that. I'm just going to add the feet right here so you know the units. And there it is. All right. So again, once you have the triangle set up, the rest of the problem is pretty much the same. Well, it's exactly the same as the kind of stuff you're doing yesterday. Let's just look at one more problem. Okay, what am I doing here? There we go. Okay. Here we got a builder is designing the roof line for a house. If the roof needs to rise 8 feet in the middle and there is to be a 24-degree slope, what will the length of the roof be? All right. So let's model what's going on. A builder is building a house. There's the roof. Here's the bottom of the house. There's the front door. Now, the roof itself is made up of a triangle right here. And so we're going to focus on this triangle right there. Come on the right side. And what I want to do, I'm not going to label this at all. I'm going to draw this triangle. And I want you guys, based on the reading there, I want you to label where the 24 degrees should go, where the 8 feet should go. And if you get that far, just find out where the missing value that we're solving for should go. So once we've got where the 24 degrees should go and the 8 feet should go, the question is, what side of the triangle are we solving for? Are we solving for the bottom or the hypotenuse? What do you think? Hypotenuse. Okay. So why did you say hypotenuse?
It's like the length of the top of the roof. You don't want the inside of the house. You want the actual roof.
There we go. So this is one where sometimes the phrasing can be a little bit weird, but I think it's pretty, maybe this one's a little clearer than the other. I don't know, it's your opinion. But the length of the roof, we know the roof is the top of the house. So I think it makes sense to think of the length of the roof as that hypotenuse. Yeah, this, just like was just mentioned, this would be more like the length of a ceiling inside the house. And we're not, so that's not what we're solving for down there. All right, so Now we can just move forward. At this point, what I'm going to do is I'm going to let you guys solve it completely from here. We got our triangle. See if you can solve for the missing length of the roof. And I'll just run through the calculations in a minute, but you guys can write the answer on the screen as soon as you find it. All right, let's go through this. I'm just going to run through the algebra and the whole trig process pretty quickly. Here's my reference angle. There's the opposite, hypotenuse, and adjacent. I'm solving for the hypotenuse. I know the opposite. I don't care about the adjacent. This tells me I'm going to be using sine, which is opposite over hypotenuse. I don't want to use cosine or tangent because both of those use the adjacent, and I don't need that. Okay, so if the sine of my angle 24 equals the opposite 8 over x, again, I'm just going to do a quick trick to kind of do a switcheroo. Turn that into x equals 8 divided by the sine of 24. Now I can plug that in my calculator, and if you do that, you will find exactly that answer that was written down. 19.6687 ... We round this to the 10ths, which is 19.7 feet. Okay, and that's all there is to it. So hopefully you guys ran through the process correctly. If those both made sense, you feel like you've got the hang of it, your homework tonight is to do 6 more problems that are different scenarios. Some of them you might find ridiculous. Some of them you might find, plausible and useful applications of trigonometry. Anyways, that's what we're going to be doing tonight. If you have any questions, you can certainly feel free to stick around. If you are good to go, you can check out the homework on Canvas and get that done with the remaining time in class. All right, if I don't see you, or if you're not going to hang around, I'll see you tomorrow.